Hello everyone, welcome to this introductory process video. I'm Vicky from Fudar Alloy, and I manage content for our global website and social media channels. Ahead of our upcoming online technical forum, this video will provide a general overview of the key manufacturing processes used in electrical content assemblies, focusing on three main areas: welding, riveting, and stamping. This video is designed as a starting point to help you build a basic understanding of these processes. In future forum sessions, our technical experts will explore selected processes in greater depth and answer your questions. Now, let's get started. Today, we will cover 5 main areas. We will begin with welding, followed by riveting and stamping. Then I will give you a brief introduction to Fudar Alloy before wrapping up with a preview of our future online session. Let's begin with part 1, welding process. The first process we will look at is resistance welding. Electric current passes through the workpieces and their contact interface. While they are held together under electrical force, the resulting resistance heat raises the material to a molten or plastic state, allowing a metallurgical bond to form. 3 parameters are critical: welding time, welding current, and applied pressure. They must be carefully balanced to produce a weld nugget with sufficient strength at the joint interface. Common methods include spot welding, seam welding, projection welding, and resistance spot welding. The process requires no filler metal, supports high production rate, causes minimum workpiece deformation, and is well suited to automation. For these reasons, resistance welding is widely used in low-voltage electrical equipment, automotive manufacturing, home appliances, aerospace, and electronics. A related process is resistance brazing, sometimes known as contact brazing in electrical contact manufacturing. Like resistance welding, it uses electrical resistance to generate heat. As electric current passes through the workpieces and the joint area, resistance heat is generated. This heat warms the workpieces and melts the brazing filler metal, forming a brazed joint. In practice, the filler metal is generally supplied as either a solid brazing preform or a brazing paste. Another brazing method is induction brazing. An alternating current flows through an induction coil, creating a changing magnetic field. When a metal workpiece is placed inside the coil, this magnetic field produces eddy current within the workpiece. The workpiece's electrical resistance causes these currents to generate localized heat in the brazing area. Several effects influence how the heat is distributed, including the skin effect, proximity effect, and ring effect. Once the filler metal melts, capillary action and welding behavior help it flow into and fill the joint. Next is in-die welding, an integrated process that combines a punch press, die, and welding unit in a single production system. The profile strip is fed and cut, then welded to the base material. The press, die, and drive mechanism operate in sync, allowing stamping and welding to be completed in a single press cycle. As with resistance welding, the 3 key parameters are welding time, applied pressure, and current. By combining these steps, in-die welding reduces the need for separate secondary processing and improves both production efficiency and process consistency. Besides the processes we have already covered, let's briefly look at 4 other joining methods. First, electron beam welding uses a narrow, high-energy electron beam to strike the workpiece. The energy of the electrons is converted into heat, melting the material and creating a weld. This process can also join certain dissimilar metals with significantly different melting points and thermal expansion behavior. Next is flame brazing. This process is usually carried out in air, so separate shading gas is generally not required. However, flux is typically added to remove surface oxide and help the filler metal flow. Common fuel gases include propane, butane, liquefied petroleum gas, acetylene, tongue gas, and natural gas. Compressed air or oxygen is normally used to support combustion. The third process is furnace brazing. Assembled workpieces with brazing filler metal are placed in a furnace and heated uniformly until the filler metal melts. Once molten, it is drawn into the joint gaps by capillary action. As it cools and solidifies, it forms a metallurgical bond. Depending on the application, furnace brazing may be carried out in air, a protective atmosphere such as nitrogen, or a vacuum. A protective atmosphere or vacuum helps reduce oxidation. Graphite fixture may also be used to hold the workpieces in position and maintain joint alignment during heating. The final process on this slide is ultrasonic welding. Heat is generated mainly by friction between the workpieces. Originally used primarily for joining plastics, ultrasonic welding is now also used to join metals. During ultrasonic welding, pressure is applied, while high-frequency vibration creates microscale oscillations at the joint interface. The resulting interfacial friction brings the metal surfaces into close contact and forms a solid-state bond. At the same time, the high-frequency motion breaks up the surface oxide fumes, allowing the weld to be completed under relatively low pressure. For the applications covered here, ultrasonic welding is particularly suitable for difficult-to-weld metals and contact areas of up to 100 square millimeters. When needed, thin layers of silver, copper, or aluminum can also be used as interlayers to improve weldability. Now that we've covered the welding processes, let's move on to part 2, riveting process. In-die riveting is an integrated cold joining process carried out within the progressive or compound die. Part positioning, fitting, and riveting are completed automatically, eliminating the need for separate secondary operations. During the process, die pressure deforms the shank of the contact rivet, mechanically locking it to the base material. The key feature is that riveting is completed directly inside the die. Depending on how the riveting force is applied, the process can be spring-loaded or manually operated. It can also be divided into top-feed and bottom-feed riveting. In top-feed riveting, the rivet head is above the copper strip. In bottom-feeding riveting, it is below. The bottom-feed method is more commonly used. The next part is stamping process. Stamping is usually carried out at room temperature, a process commonly referred to as cold stamping. A stamping press and die apply force to sheet metal, causing it either to separate or undergo plastic deformation. This produces a part with the required shape and dimensions. The stamping process includes two basic types of operations. The first is separation operation, such as blanking. In this process, the sheet metal is cut along a defined contour to produce the required shape and size. The second is forming, where the sheet metal undergoes plastic deformation without cracking to create a desired three-dimensional shape and dimensions. To ensure a stable process and consistent quality, three core elements must work together: the stamping press, the die, and the metal raw material being formed. That concludes our brief overview of welding, riveting, and stamping. Before we close, I'd like to give you a brief introduction to Fudar, including our development, business scope, manufacturing footprint, and global reach. Let's begin with a brief look of how Fudar has grown over the years. Fudar Advanced Material Group was founded in 1994. In 2025, the group recorded $7.9 million in revenue, up 28% year-on-year, while its silver usage reached 500 tons. By 2030, we aim to achieve annual revenue of $1.5 billion. Fudar Alloy is one of the group's core businesses, focusing on the research, development, and manufacturing of electrocontact materials. Between 1994 and 2008, Fudar developed materials for magnetic latching relays, introduced the silver graphite production line, and brought eco-friendly silver tin oxide electrical contact materials into mass production. Over the next decade, from 2008 to 2018, we expanded into higher-end and more specialized applications, including contacts for automotive relays and railway signal relays. One notable milestone was becoming the sole supplier of communication and control contacts for China's high-speed rail and urban rail systems, giving Fudar Alloy a 100% share of this specific market. Since 2018, new energy and 5G applications have become important growth drivers. We have also continued to develop products and manufacturing processes for large air circuit breaker assemblies. Building on this development, Full-dark alloy now serves a broad range of electrical and energy applications. Our products are used in wind and solar power generation, data centers, rail transit, 5G communications, smart buildings, new energy vehicles, and industrial control. To support these diverse applications, Full-dark's business is organized into three main segments: electrical content materials and assemblies, precious metal recycling, and stamp and cold forged parts for the new energy industry. These three business segments are supported by four manufacturing bases. Together, they cover a total site area of approximately 110,000 square meters and a total building area of around 168,000 square meters. As a general electrical alloy material business unit, we produce contact tips, powder metallurgy contact tips, glass strip, profile materials, and brazing materials. The Electronics and the Electrical Alloy Materials Business Unit, which is also home to our headquarters, mainly produces silver alloy wire and contact rivets. Our Electrical Components Intelligent Manufacturing Business Unit focuses on contact assemblies. The fourth base, Zhejiang Weijia Precious Metal Powder Material Corporate Limited, is a wholly owned subsidiary that produces silver powder, cold and silver plate, and silver-coated composite powders. Together, these manufacturing bases give us large-scale production capacity across a wide range of electrical content materials and assemblies. To give you a sense of our scale, each month we can supply up to 500 million contact rivets, 45 tons of silver alloy wire, 15 tons of contact tips, and 20 tons of powder metallurgy contact tips. Our monthly capacity also includes 3 tons of brazing materials, 10 tons of glass strips, 4 tons of profile materials, and 100 million contact assemblies. Across this product category, we support customers at multiple levels, from basic materials and individual contacts through to complete assemblies. This allows us to provide tailored solutions based on each customer's product design and specific application requirements. This production capacity supports a growing global customer network. Today, Full-dark Alloys export its product to 32 countries and regions worldwide, with offices and local business support in Europe, India, and other key markets. We work closely with customers across the electrical industry, both in China and internationally. Finally, let me give you a quick preview of what comes next. For an upcoming live session of Full-dark Alloys Online Technical Forum, we plan to select one of four processes: resistance welding, resistance brazing, induction brazing, or in-die welding, for a more in-depth presentation led by a Full-dark technical expert. The live session will include a Q&A, giving you the opportunity to ask questions and exchange ideas with our team. The specific topic, date, and time will be announced on Full-dark Alloys linking page, so please follow us for updates. If you have any specific requirements or electrical content materials or assemblies, or would like to learn more about any of these processes, please feel free to contact us through our website or linking page. That brings us to the end of this introductory process video. Thank you for watching, and we look forward to connecting with you during an upcoming live forum session.